We're going to start here with basic power generation and start seeing if we can work out some details on how we humans get all of our power and do all our work with all of our electricity and all that kind of stuff. The basic main way we generate electricity on a large scale is to ultimately uh, either through nuclear material or burning some sort of fuel, garbage, coal, something like that. We basically get heat. And then we take that heat and we use it to heat up water, put it into water, turns it into steam, and then we push that water into a turbine. Basically, just a big blade that you shove hot water through, use the heat of it to move, and it'll spin this. And that spins a giant magnet, and that giant magnet is spun near a big coil of wires, and that big thing is called a generator, and then you get electricity. That's the basic way. Uh, the big part of this is how do we get the heat, and that's our main two things we're going to look at here. First, before we get way too into that, we need to talk about something called a Sankey diagram. And this is a way to look at some sort of process and ultimately tell its efficiency or basically where all the energy is going. Now, these can be drawn in many ways. You can have waste energy going toward the top or toward the bottom or out the right or whatever. But the one I'm about to draw, I'm going to say everything that goes down, points downward, is wasted, and I'm like want to do my fingers as quotes on that wasted energy. And then everything that comes out on the right will be energy that was actually useful, and everything coming in from the left is what we start with. So basically, we're going to start with our thermal energy. Thermal energy, and it's from some sort of source like a boiler or something like that. But some way we get some sort of thermal energy, and we'll have, let's say, this amount of energy. Now you have to keep these things to scale. So if I start with this amount of energy, I would normally be doing this like on a chart with a scale here, and I could literally read the vertical axis. Like, so I could have something like this, a vertical and horizontal axis, and I could read the vertical axis in here and say, that's whatever this is, that's how much energy I had to start with. Okay? And then I could come over here and I could have a line coming off the bottom, an arrow, and it could look like that. And this could be like energy lost to the environment. So this is lost to the environment. So this would be like up here where I talked about the water. We heated the water up, but then before the water made it in the turbine, it started condensing, it started cooling back down, which means it was losing that energy to the pipes or systems or anything like that, to the air around it. So this is energy lost to the environment. It's everything cooling down. Sorry, I squished the word environment in there. So it's it cooling down, and then that reduces the size of this. So this arrow on this side would have to be up a little bit higher, like an equivalent to scale amount that this is. So, if this was 100 joules and this was 20 joules, then this distance here from this point to this point would have to then be 80 joules. So if this was 100 and this was 20, this would have to then be 80 or something like that. So you have to make sure you keep it all to scale. And then you could come over here and you could have another energy loss, like say due to friction uh, in the gears and stuff of your system. So this would be the energy lost due to friction. So this could be like moving parts of your generator or moving parts of your turbine rubbing up against each other. And then of course we have to reduce the overall amount of energy we had there to begin with. And then you could come over and say had another little energy loss. And so all these arrows that point down, these are like little energy losses, right? So we could have another one, maybe a thinner one here. Bring this up just a little bit. And you could look at the width of these things, come straight down, straight down to here and look at what this actual width is. Not the width of the arrow, but the width of the thickness of this line here, this distance across, and tell how much energy was actually being lost. So this could be like energy lost due to the generator itself, like electrical energy. So this was lost due to generator. And this is like a back EMF or resistances in the wires and things like that that would slow it down. And then what you'd be left with is something coming out over here, and this would be the actual like energy that you got produced in electricity. This would ultimately be like your electricity you produced, and that would be what you got that was useful that you could send out to customers and stuff and have that electricity there. So you'd have something like this. I know my drawing isn't great, but the key things you need to remember about it is you need to, of course, label what each arrow is, and you have to do it to scale because you should be able to look at this diagram and ultimately tell me how efficient this was. So maybe I got over to here and I look at this and let's say this was 100 joules. So let's say that this was 100 joules, right? And then I looked over here, by the time I got here and I measured the distance here, over here on my scale, and I saw that it was like 40 joules. Well, then I know that this was 40% efficient because I know that the energy I got out of it minus all that was lost, which was our energy we got out of it after we took away everything we lost, over the total that was input, and that'd be our efficiency. You'd have 40 joules over 100 joules, and that was our definition of efficiency from before. Okay, so these kind of diagrams, you have to kind of look at them a few times. You can Google search up some of these diagrams. There are going to be a lot of them that are way more complicated than what I've shown here. Sometimes the arrows might be pointed up. Sometimes all the arrows just go all the way across, and then it just labels over here what they all went to. But this is the basic idea. You label it, you keep it to scale, and it shows you where all the energy is going and flowing and where it's lost and what happens to it. Okay? Next thing is, and I'm not going to sit here and go over all these because it's kind of a waste of time in the video, especially since it's just a list in your book, is I want you to hop in your book and look at the advantages and disadvantages. Misspelling that. Disadvantages of the different types of power systems in your book, power generations, but most specifically, there's some for everything, but really you want the thermal power generation. That's going to be your burning of coal, your burning of fossil fuels, your burning of garbage kinds. You're going to have your nuclear power, and you can also have you'll also have your more renewable types like your wind energy or your solar. So those kind of things, I want you to look in your book and find those because I don't want to spend a lot of time sitting here trying to talk about those different things. I want to be a little more specific. So up here before, all you really need to do is remember that you burn something, you heat a turbine, or you heat water, that water turns into steam, the steam gets pumped through a turbine, turns a turbine, generates electricity, and so that's pretty standard for thermal. All you're doing is burning something, but how does that work with nuclear power? So how does that cycle work with nuclear? And really the only part that changes is the part at the beginning of how you generate the heat. So I'm going to keep this a little simpler than what you might find in your book or elsewhere, where I'm only really going to talk about the actual heat generation. And you can look at the illustration in your book or online for a little better picture than I'm going to be able to draw here of a nuclear power reactor. But the big main things you basically need to know is you got some sort of pressure vessel. Inside that you have nuclear material. It's heating up as the nuclear reaction occurs. Energy is given off. You use that heat from inside that pressure vessel to heat water, and the water turns a turbine, and the turbine turns a generator, and you get electricity. So the same basic pattern. So let's just talk about how do we actually generate and control the generation of that heat. And so the main things for that you need to know are, well, first thing is control rods. These are literally big rods that can be put down in between the nuclear material like uranium or plutonium or whatever it happens to be, and it blocks the little neutrons that are emitted by one from going over and hitting the rod next to it and causing and continuing the radioactive decaying that's occurring. So these control rods can literally be lowered into place, and it basically it's a material that stops neutrons, and you can lower them a little bit or amount, and you can use them to control the nuclear reaction rate. Control the reaction rate, the nuclear reaction rate. Okay, if you let it get too out of hand, then you have your nuclear power plant melting down, and that's not good. But if you shut it off too much, then you're not getting enough power, so you have to use these to control them. Then the second thing you need to know about is something called a moderator. So what this is usually a small molecule substance that slows down neutrinos but doesn't fully absorb them. So what this is usually is graphite or heavy water. Heavy water is just H2O, but instead of the regular hydrogens, you have the deuteriums, which is just an isotope of hydrogen. So heavy water. And this heavy water, I think this is probably my understanding of it all is this is the better way to do it is with this. But essentially, you're putting this between all your nuclear material, and what it does is it slows the neutrons down, because as it stands, most of the neutrons produced in decay from one rod going to another are going way too fast to be absorbed. They have too much energy to actually get in and collide with the nucleus. They would just shoot right on through and not be caught by another nucleus to continue the reaction. So they're way too high of energy. And so your basic setup is you put your fuel rods, they're called, I guess I should put that, the fuel rods. These are your actual, this is your actual nuclear material. And so you have these fuel rods that are all next to each other, right? And it's your fuel source, like we talked about in the previous video. And the little neutrons get shot out from one and they go and hit another. But if they're going too fast, they don't collide with the next one. They pass on through. So you put what's called a moderator in there, and I'll use yellow for that. You put a moderator in between them. And this moderator slows those neutrons down so that they're low enough energy to actually hit the next rod's, the nuclei in the next rod, and continue, so that's the moderator. That green was the fuel rods to be specific. And it'll actually slow it down so that the little neutrons passing from one to the other, they get slowed down, and then they can actually have this, this reaction occur, of neutrons passing back and forth. Now, what do you want to do if you want to slow this down? So I'll do maybe blue for this. What you have are the control rods, and these are other rods that can be raised and lowered. These are your control rods in blue. They can be raised or lowered down in between these to block some or all of the reaction going on. And so all these things, they can be, I know that my drawing's really bad there, but they are all just, they lower them down when you want to reduce the reaction, and you raise them up when you want to increase the reaction. So you have people there that are watching and determining how hot everything is getting and everything like that, and then they move these up and down to control it. Now, this moderator, like I said, could be graphite. You could put that in there. But the other thing that I've always heard was the better option was this heavy water. And the reason for that is because when you use heavy water, it also doubles as a cooling mechanism that transfer heat, but it also keeps the cool rod's fuel cool. So the idea behind heavy water is it's supposed to help with having a nuclear meltdown. Because what would happen is if this started to overheat, the water would evaporate. Right? The water would start to evaporate. And if the water evaporates and leaves, then there's less moderator there. So as the water levels would fall, the moderator would leave, which means these neutrons coming out would have too much energy, and they'd pass right through each other, and then the reaction would stop. So this heavy water, as my understanding is basically makes it a nuclear power plant that can't melt down on its own. Now you could have something like an earthquake or something like that hit it and break these open and be bad. But with the heavy water, it basically is like fail-safe. It's like an extra layer of protection where if it gets too hot, the water evaporates, the nuclear reaction stops, and it cools back off. So my understanding is this is actually a better, safer way to do it, to make sure that nothing gets out of hand and you don't have that have it melt down. So you'd have this all inside some closed vessel. It would create heat, right? Heat, and the heat would then go to water, and you'd pump it into water, and the water would turn a turbine, and the turbine turns the generator, and you get electricity. Okay? So those are our main ways that we produce power. But both of these ways are what are considered to be non-renewable sources of energy. So these are non-renewable energy sources. And what that basically means is that we consume this energy source. It's consumed faster than it's replenished. All right? It's consumed faster than it's replenished. The things for this are things like oil, coal, things that we believe took, a long, long time to be made, and now we're using them up, and we're using them faster, a lot faster than they can be reproduced, so you'd eventually run out. And then the other type, which we're going to talk about now, so this was the first thing we were talking about, is renewable energy. And in this one, it's the opposite. This is consumed slower than it's used, than it's replenished, not than it's used. It's consumed slower than it's replenished. So this one slower, this one's faster, which means that we should be able to refill our sources of this before we would run out. Examples of this would be basically any energy source that comes from the sun, wind energy, if there's hydroelectric energy, solar energy, all of those kind of things that we can renew faster or are renewed naturally faster than we can use them up. And so the first one of these we want to look at is the wind turbine. Now, this is supposed to be something that's, this great thing where we're replacing fossil fuels, but you have to keep in mind there's still a chance that these things it can have somewhat of a negative impact because, maybe we get so many wind turbines on the planet that we're removing so much wind from the atmosphere that no storms are traveling anymore, and it's causing droughts in areas because storms aren't moving around anymore, and cold fronts aren't moving, and rain isn't coming across the land, it's staying just out over the water or something. So you still have to be careful, even with a renewable energy source. There can be potential negative downsides to it. So it doesn't, just because it's renewable doesn't make it the best idea to necessarily use in large quantities and use a whole lot of. Now what we're about to talk about is the ideal case. So this is the ideal case where it's almost like it's a maximum that we can't even reach, where it's ideal situation where all kinetic energy is removed from the wind. Now this is not possible because you can't stop it fully. One, it'd have to be 100% efficient type thing at converting it, and two, if the wind went into the turbine and totally stopped, then it wouldn't be able to get out of the way for the next bit of wind to come through. So it's not a possibility to do this. So essentially, when you have your wind turbine, the blades will sweep out a circular area, whatever the blades happen to look like, but they make this big circular area, kind of looks like a flux capacitor there, as they spin, right, as they're pushed by the air, and it's this area here that determines how much air is actually going through it and how much energy we can take out of that air, and then of course how dense the air is will matter. So the area of this circle matters, the density of the wind is going to matter, and then of course the speed of that wind is going to matter. Slower moving air has less kinetic energy than faster moving air, and we can work out that the power that we get from this is 1/2 rho, the density of the air, the area of that wind turbine, of the blades, times the velocity cubed. Okay, and so that's our equation for this one. It's one you really need to know how to use. You're given it, I believe, so you don't have to memorize it. But it's essentially density of the air, area of this. So if you like knew the length of a fan blade, that would be your radius, and you could calculate out the area of the circle that it covered, and then the speed of the air actually going through it. Okay, and so this will give your this will be your equation here. All right, that's pretty much it for wind turbines. The next one we can talk about then after a wind turbine is a hydroelectric dam. This one's hydroelectric dam. We'll just go with hydroelectric power. So hydroelectric power, I guess it doesn't necessarily have to be a dam. I was going to write dam, but this could also be like a lake at the top of somewhere that we're siphoning water up. So let's just do hydroelectric power. And the way this one works is the idea is basically if you have a large enough container of water, okay, such that when you put a little spout low down on it, right, and the water comes out here, if it's coming out, if this little area that you're taking it out of is small compared to up here, such that the amount that the water drops is negligible compared to how fast it's coming out, then what you basically end up finding is that the kinetic energy of the water here, the kinetic energy at the bottom of the water shooting out, is equal to the potential energy of the water at the top. And so what I mean by that is, if I measured the speed of the water coming out here, it would be the same speed as water would be going if you just dropped it from that height. So whatever this height happens to be, h, if I dropped it from that height, however fast it would be going after it fell that height, is how fast it would be shooting out the side here. And so we could take advantage of that with dams or a lake that's up high that we could drill down and siphon water out of the bottom. So you put a dam here or something, you pile water up over here, you let the water come out of the bottom of the dam, and you take that energy, you push it through a turbine, it spins the turbine spins a generator, and you generate electricity. There's a big magnet near some coil of wires inside that generator, and you ultimately get that. So basically what happens is you'll have the energy that's stored that you're going to get out of this, and again, this is assuming 100% efficiency, that you take all of the kinetic energy out of this water at the bottom. But again, just like up here before, it's not possible. We can only get a fraction of it. All of that energy you start with is mgh, however high the water is above this. Oh, and another thing, for this staying at the same height, you either have to have a really big surface area up here compared to what you're taking out here, or you can have it be more like in a reservoir or a dam behind a dam where it's being fed by rivers, and so it keeps replenishing and refilling itself, so this level doesn't really change or doesn't appreciably change while you're doing this. So just keep that in mind. If this is dropping really fast, like if this was a really skinny container and the water was dropping out real fast, then this wouldn't hold anymore. This little top here has to basically not really move very much. It has to stay at that same depth, or it gets a lot more complicated. So this is mgh. I can replace rho or m with density times volume, and I'll have that, and then I'll have the g still there, and now the height. The height we're using was just height, but if we let all of this water empty out, like if we just let this all go, then essentially that would be like having something at h over 2 fall. The center of mass would be in the middle at h over 2, and it would be equivalent to letting that fall, all of that water fall a distance h over 2, because the stuff at the top falls all of h, but the stuff down lower doesn't fall all of h. So effectively, it acts as though it all fell from the center of mass, which gives us now a height of h over 2. The volume can be replaced by the area, the surface area at the top, times that height. That would be your volume. So area g, and then if I take that height and combine it with the other one, then we have h squared over 2. um, and do a little rearranging, and you get a little bit more useful form of this. Density of the water, A GH squared. Okay? And so this allows you to do some things where, you can look at this and tell, how much energy could potentially be taken from this dam. You're also going to be expected to be able to figure out what, how much power you might get from one of these. So you might get a question that tells you like that, tells you all these properties of the dam, but tells you it's like 30% efficient, in which case you'd have to calculate this total energy from before, either with MGH or one of these from along the way, and then take 30% of it. So be prepared that you might have to do something like that. And then the last type we have is solar heating, solar power. So solar power. And there's two main ways you can get this. One, the photoelectric effect. This would be solar panels or solar voltaic panels. So solar power, solar panels. These take, light hits them. You have a panel, right? You've seen these before. Light comes in and hits them and creates electricity. That's pretty much it. You get electricity out of it. We've done that plenty of times. You should know how that works. And so these work pretty well. Big problem that might be with this is you're taking, if we put these everywhere, we'd be essentially trapping every bit of light that came from outer space here and turning it all into electricity, which ultimately just creates a lot of heat. So again, you kind of have to use these in moderation as well. And then the other type is just actually letting the solar, the heat from the sun, heat up a fluid. And so you might take something like, you put a big pipe system around, and you have a bunch of pipes, right? So pipes full of some water or fluid or something, right? And then you put in water at the top, and you have the water flowing here, and so you'd have cold water here and hot water here. And so what you do is you let the sunlight come in and actually heat that water up, and that can cause, a convection that would occur as the water would then circulate around, and you can use that water to get heat from it. I know people have this kind of set up on their roof. You can use this to heat your house or heat a swimming pool and things like that as well. Okay, well that's the basics of all this power generation for this topic part here, and that's all we've got for now.